This is class number 11 on ultrasound imaging. Both radar and sonar render the ranging information in the form of a 2D image. But how you turn the echo of a beam into an image? Well, you scan the beam. Ultrasound has become a household term, and when it's heard, the image that comes to mind is this one. For now, the scanning works pretty much as it can be intuited. At every boundary where there is an impedance change, part of the beam will be scattered back to the receiver at the time that is proportional to its depth, and that will be the x coordinate. The beam that is being switched on would be the y coordinate. But there's so much beyond intuition. For instance, there's a lot of physics here. This particular one is a convex switch array transducer. Main features: footprint of 50 millimeters, bandwidth 2 to 5 megahertz. Applications include obstetrics.
Megahertz?
Of course, if a sonar uses up to 100 kilohertz for resolving centimeters in depth of several meters, then for medical ultrasound, where we need millimeter resolution in some tens of centimeters, the wavelengths must be at least one order smaller, and so the frequency must be 10 times that of 100 kilohertz, and that's in the range of the megahertz, right? However, many specialized ultrasonic transducers have been developed for different tests. And there you have the convex, the linear, the phased array, microconvex, T-type linear, the biplanar, endocavity, and the intrarectal.
That last one sounds like a lot of fun.
You could request, say, a convex for even greater fun, right? Here are the main components all transducers have inside: the piezoelectric element, backing material, acoustic matching layer, and the acoustic lens that narrows the beam in the vertical plane. Also, there's the wiring that feeds electricity to the piezoelectric crystal elements. Beginning with the star of the show, the piezoelectric crystal, that as technology has evolved, it has shrunk further and further. The speed of sound in piezoelectric ceramics is about 4,400 meters per second, so the wavelength for 2 megahertz will be 2.2 millimeters. A crystal with a thickness of L equal 1.1 millimeter will hold half a wavelength of a 2 megahertz sound wave. Such a crystal will show a fundamental resonance at 2 megahertz, but it will also show resonance at 4, 6, and so on. These resonances, especially the fundamental, would have a narrow bandwidth if the crystal could expand and compress freely with no energy losses.
Why especially the fundamental?
Because as the frequency increases, it becomes less nearly to no energy losses. This is the reason for using quartz oscillators in timepieces. That expanding and compressing freely can be expressed more precisely in terms of the acoustic characteristic impedances. Z equal rho Z, where rho is the density and C the speed of sound. This will happen only if the characteristic impedance of the piezoelectric crystal Z sub P is much higher than that of Z sub B and Z sub A. The MKS unit for acoustic impedance is the rail, kilograms over meter square per second. The harder and heavier the material, the larger the acoustic impedance. Piezoelectric ceramic impedances start at 30 megarails with PZT.
What does PZT stands for?
PZT has to do with lead zirconitinite. It's the most used piezoelectric ceramics for ultrasound transducers. It is the preferred choice for being physically strong, chemically inert, and relatively inexpensive to manufacture. Did that help?
PZT has a perovskite crystal structure, each of which consists of small tetravalent ion in lattice of large divalent metal ion.
Sebastian, stop. Enough. However, sharp resonance is the very opposite to the case of a piezoelectric ceramic in transducers, where it's sandwiched between a backing material and the impedance coupling layer to the acoustic load. Though the backing material will reflect most of the wave power, the zeta coupler, being designed to eliminate as much reflection from the load as possible, will not allow a sharp resonance, since most of the power goes to the load, which in this case is the patient's tissue.
Oh, power to the patient.
Oh, come on, that one was way below your standards. Well, maybe we need more on this backing material. The backing material should have a small impedance, so that it reflects the most, and whatever it may transmit should get attenuated. Also, if conductive, it could serve as a common electrode. One of the most used backing materials is the E-solder 3022. It has a good electric conductivity, making it possible to be one of the electrodes of the transducer element. This material also has low acoustic impedance, 5.92 megarel, when compared to a piezoceramic crystal that has more than 30 megarel. Such a boundary would be reflecting about half of the ultrasound power. It also has high attenuation, 120 dB per millimeter at 3 MHz. You don't want ultrasound propagating to the back of the transducer housing. Cables there being bent millions of times per second will not last too long, right? A lot of the physics magic goes into this last component, the zeta coupler. The acoustic load is the human tissue. It is a lot softer than piezoceramics. The former can push or pull very hard, but move very little, while the tissue needs it softer, but a larger displacement. The impedance coupler must perform the function of a lever. Though magicians never reveal their tricks, fortunately, scientists do.
Once they have filed their patents, of course.
Very funny, very funny. And here's what they came up with. The crystals were coated with a layer quarter wave thick. Let's check transmissions and reflections. Part of the piezo wave is reflected. Part of the transmitted wave into the coupling layer is reflected from the tissue. Part of this reflection is transmitted into the piezoceramic, but delayed 180 degrees. If the impedance of the coupling layer equals the geometrical mean between the ceramic and the tissue, bang, magic happens. Reflected piezo wave is cancelled. Let's look at the process in more detail. Piezoelectricity generates a wave in the ceramic. Part of the wave is transmitted into the zeta coupler, but some energy is reflected back. Same happens at the border with the tissue. By the time the wave reflected from the tissue arrives back at the ceramic boundary, the displacement wave entering the zeta coupler is perfectly in phase with it, so they add up. Part of that wave from the tissue also gets transmitted into the ceramic, but in counterphase with the one being reflected in that boundary, so they subtract. The process repeats, and the standing wave in the zeta coupler gets larger while the reflective wave from it gets smaller. That will continue to happen until the power leaving the zeta sub m region equals the one entering it. At this point, if the impedance of the coupler equals the square root of the product of the ceramic and the tissue impedances, then the reflective wave will cancel.
How did they figure that such an impedance value did the trick?
Hey, we're believers here. You're calling for a ton of math to come and spoil the magic.
A little math cannot hurt.
Oh my God, here we go.
So the question is where this expression comes from, right? Okay, let's go again over those waves. We're going to need a coordinate reference. Here it is. And here's the steady state exponential expression of the transmitted pressure wave.
And where does that come from?
From class 3 and forced oscillations.
I must confess that, though I hate to admit it, Sebastian's right. We discussed Euler's exponential notation back in class number 3. Reviewing it will take too long, so let's continue. This expresses in exponential notation, of course, the reflected wave.
And what about that there?
That was discussed in...
Sebastian, you're not taking my line this time. That is Fresnel's reflection coefficient that together with the transmission one was discussed in class number 9. And now we can express how much the pressure swings at any value of x within the zeta coupler region. We can do the same for the velocity wave. It has the same expression as the pressure. However, the reflection coefficient for the velocity wave is negative to that of the pressure. Yes, that was in class number 9 too. The expression for the velocity swing as a function of x is the quotient of the pressure over the velocity at any point x renders the impedance that the incident wave from the ceramic would see if the boundary happened to be at a distance x from the tissue. The ratio of the amplitudes of the pressure over the velocity within the zeta coupler is zeta sub m. Also, we all know the Euler's identity, right? Right? Now, after some boring algebra that you can do on your own, we come to this equation. If we took the limit of the impedance for x tending toward lambda over 4, it would be that of zeta sub m squared over zeta sub t, a real number. Now, we want this number to match the characteristic impedance of the ceramic, zeta sub c. Now you know where the expression comes from.
Whoever came up with this was a real genius.
As Thomas Edison once said, genius was 5% inspiration and 95% transpiration. I'm sure that making this idea work took a lot more than deriving the equation. This trick is older than ultrasound transducers. Quarter wave coatings have been used for reducing reflection in optical lenses. Since the early days of radio, quarter wave impedance couplers have been common technique for matching the standard transmission lines to the antenna impedance. And there's a long list: solar cells, LEDs, TV screens, microwave circuitry, bass boosters and sophisticated speaker system, and probably a lot more that is not presently coming to mind. Quarter wave couplers have a problem though, And it is that they only cancel reflections perfectly for that frequency, that water wave of which has the right size. Ultrasound short pulses required some bandwidth. Besides, the capability of changing carrier frequency is a desirable feature in transducers. Using more than one layer allows widening the band, but the math thickens. There are novel approaches with more technology and less physics that involves the nano word. Nanotechnology promises direct coupling by simply allowing the area ratio to do the matching.
I still have a problem with this data coupler, and it is that there's an acoustic lens, and maybe even some protective plastic, before any wave hits the tissue.
Ceramic impedances are beyond 30 megarails, and the human tissue is only about 1.4. Plastics are 5 to 3 megarails. If a coupler makes it down to that, it has already made a good job. And there will still be some megarails left for the lens to work its magic. See? There's another transducer with beautiful physics, the phased ultrasound transducer. It has fewer piezoelectric ceramic chips, a lot fewer. So it's much smaller, but it is still capable of scanning the same sector as the convex switch array transducer with the same lateral resolution. Its principle of operations go back to good old Huygens. Each point in a wavefront becomes a new source of waves. Why not set the wave point sources with the phases of the wavefronts we need? Changing the phases will make the wavefront change direction with no moving parts. Great idea, right? The implementation of this idea requires a lot more electronics, though. A switch array needs only one transmitter, one receiver, and a switch for firing one crystal at a time. Whereas in a phase array, all crystals must be driven simultaneously. Here's a little history, and this is how early phased arrays looked like. It all had shrunk into this, and so had the price in the same proportion.
Wow.
Microcomputers can do more than just change direction of the wavefront in a phased array. It can also reshape it. For instance, it can focus the beam at any desired depth. Here's an animation. The small footprint allows looking between the ribs. Also, phasing and switching may be combined. Here's an animation. And here's an animation of the linear array. Though there's a lot of physics in transducers, there's some in the reflection, refraction, and backscattering of ultrasonic waves returning from the tissues or industrial samples under inspection. Here are common echoes from human or animal tissues. Hyperechoic. Those are strong echoes, reflected from high impedance surfaces like bones, tendons, or the diaphragm, that show us clusters of white dots. Isoechoic. Those are weaker echoes, resulting from the scattering of the inner textures of most organs, that show in gray. And there's the hypoechoic or echo-free areas that show in black, from where there's no texture or particles large enough to scatter, the case of urine, blood, or liquid in a cyst. Understanding the physics allow interpreting the sonograms. Bright lines show at the boundaries of different impedance regions. Gray areas show from scattering within. Interpreting the image in the sonograms require the understanding of the artifacts. These are features of the image that are not present in the tissue. They are mirrors, shadows, enhancements, reverberation, comments, refraction, you name it. With the physics we have already covered, all the artifacts in the sonograms may be explained and will be exercised in the quiz.
Quiz?
Yes, quiz. Well, it's that time. Time for the quiz. Here the answers will follow the question or problem, but hit pause and try answering it first. Problem number 1. Which field of view corresponds to which transducer? Hit pause and try your own choices. There are two fields of view with sectorial scans and the other with a linear one. Obviously, the latter must correspond to the linear scanner. One of the sectorial transducers has a small footprint and should go with a field view that shows the smallest. There's only one field of view left and it's still sectorial scan, so it must correspond to the unassigned transducer. Easy, right? Problem number 2. These are 3 ceramic crystals that operate at 1, 2, and 5 MHz. Which is which? Hit pause. It is the space between the metal plates that determines the operating frequency. The thinnest corresponds to 5 MHz, the thickest to 1 MHz, and the last is the one operating at 2 MHz. Problem number 3. Say what is more desirable for a backing material in an ultrasound transducer. Hit pause. Only the acoustic impedance, the electric conductivity, and the attenuation are important in a backing material. The rest have nothing to do with it. Problem number 4. Would the cedar copper work its magic backwards? Hit pause. It does. Nowhere in the derivation of the expression for the impedance zeta sub m, it was assumed that zeta sub cc had to be greater than zeta sub t. Actually, that is the pass of the echoes to the receiver, and it works. Problem number 5. Would the width of the zeta copper coating work with 3/4 lambda instead of 1/4? And with the same zeta sub m? Explain why. Hit pause. The impedance exhibited by the zeta copper boundary was this. The limit when x tends to 1/4 lambda renders zeta sub m squared over zeta sub t. And we wanted that to be equal to zeta sub c. That took us to the beloved expression. The limit when x tends to 3/4 lambda or 5/4 lambda or n quarters of lambda is the same, so the magic will still work. Problem number 6. Consider that there's a bullet lodged in muscular tissue. Which of the linear fields of view shown could you expect? Hit pause. It is C. The bullet generates a clean shadow artifact. All sound waves will be specularly reflected, so no echo can come from behind it. Problem number 7. Choose the best explanation to this artifact in a sonogram of the pleura. Here, two dense membranes in contact with each other should show us a single bright line, but there are three. A. The two lower hyperechoic lines are replicas of the first that show equally spaced by twice the membrane's depth. B. The two lower hyperechoic lines are replicas of the first that show equally spaced by the membrane's depth. C. The two extra lines are the peaks of a standing wave that creates between the pleura and the bottom of the lung. Hit pause. It's A. It must be twice because the reflection from the skin must go down to the membrane and up again to the transducer. The standing wave thing is total nonsense. Finally, problem number 8. Echoes coming from deep into the tissue grow fainter, so the gain of the receiver must be increased with time not to miss those late arriving echoes. Select the best explanation for this enhancement artifact. Here's A. The dark area is liquid in the bladder acting as a lens that concentrates the ultrasound wave on the tissue below. Here's B. The dark area is liquid in the bladder where the ultrasound travels faster, allowing echoes from the tissue below to arrive earlier and catch a greater gain. And C. The dark area is liquid in the bladder that does not attenuate ultrasound as much as the tissue, resulting in stronger echoes from below. Hit pause. A. Nice try. But an enhancement by a lens should show some focusing. Here the brightness is divergent. B. Way off. Earlier echoes gets less gain. C. That's it. Within liquids there's very little scattering and not great impedance change at the boundary, so more energy than expected by the gain compensation arrives at that depth. And this will be all for class number 11, which is what I humbly consider to be the least every physicist or engineer should know about ultrasound imaging. Even those who can ace the quiz may still be far from being an expert like Master Carlos Lopez, application manager of Samsung Ultrasound for Latin America, which has kindly advised on the contents of this video. We must also thank the physicist and musician Dualism of Daniel Stolik for the beautiful background music. We are near the end of this course, but we need to take a peek into that of sound in periodic structures, or into what happens when you add motion to the mix, and when that motion goes beyond the speed of sound. Subscribe to the channel.